Welcome. In this session, we are going to look at a new technique of differentiation, what's called implicit differentiation. It's called by this name because it's used to differentiate functions defined as solutions of equations rather than given in the form of an expression in the variable. Those are known as explicitly defined functions. So for example, the equation 1 plus xy cubed equals 3x squared defines y as a function of x. Or if we take ln x plus ln y equals x plus y, that's another equation. Now in doing this, we'll assume that there is a function which solves this equation. That may not always be true, although in applications there may be other reason why you think it's a function. Then there's a question of, is it really differentiable? There is something called the implicit function theorem which allows us to answer this question. But that involves things we will see in chapter 17. For now, we will just assume that that is the case and then just look at how to calculate the derivative. We have sort of used this method to differentiate e power x. We rewrote y equals e power x as ln y equals x. So that's an example of an implicit function which can also be written explicitly. We won't always have the luxury of doing that, so sometimes this method is necessary. The method we are going to use is essentially same as what we did in differentiating e power x. You differentiate both sides of the equation treating y as a function of x and then solve for y prime. It's easier to describe the method in detail if you work with an example. So let's take the example 1 plus xy cubed equals 3x squared. I differentiate both sides with respect to x. And I do this using the same process we have been using. Start with the outermost operation, apply the rule for that, and continue inwards. As you do this, eventually one of two things will happen. You come to a simple function, power, exponential, or logarithm, which involves just x, then you differentiate as usual. Or it involves just y, then you have to use the chain rule. So it will be a composition of y with some function, and the derivative will be derivative of the outside function times derivative of the inside, which is y prime. So in our example on the left, I have two terms, so I differentiate term by term. The second term is a product, so I have to use the product rule. The first factor is x, so I get derivative of x times y cubed plus x times derivative of y cubed. On the right hand side, I just have 3x squared. Of course, 1 is a constant, so derivative is 0. And then derivative of x with respect to x is 1. So I just get y cubed, 1 times y cubed is y cubed. Then I have plus x plus y cubed prime. Remember, prime means differentiate with respect to x. So it's like I have some expression to the power 3. So I have to use the power rule and the chain rule together to do the differentiation. If I differentiate for the exponent 3, I get 3 times what is inside, what's the base of that power, to the power 3 minus 1 or 2. Since I have y cubed, when I differentiate for the exponent 3, I get 3y squared. But now y is a function of x, so there is something in there which we don't know. I have to multiply by its derivative. Since I don't know what it is, I will simply write y prime. On the right hand side, I have just 3x squared, its derivative is 6x. Now I solve this equation for y prime. So subtract y cubed from both sides, divide by the coefficient of y prime. 3xy squared y prime is 3xy squared times y prime. If I divide by 3xy squared, I get y prime. Let's look at another example, ln x plus ln y equals x plus y. I'm going to use the same technique. So the first step is the same. On the left, I have two terms, so I differentiate term by term. First term has just x in it, I differentiate as usual. Derivative of ln of x is 1 over x. Second term is ln y. So it's ln of a function. So I have to use the chain rule. First I differentiate the outside, which is ln. It gives me reciprocal of what's inside, or 1 over y. I must multiply it by the derivative of the inside. The inside is y. I don't know what it is, so I simply write down y prime. On the right, also I differentiate term by term. The first term is x, its derivative is 1. Second term is y, its derivative is y prime. Note that now I have more than one term with y prime in it. I treat this as a literal equation for y prime and then solve for y prime. Since it has fractions, let's get rid of denominators. I'm going to multiply both sides with a common denominator xy and also distribute it and simplify that. That leaves me with y plus xy prime equals xy plus xyy prime. I'm going to bring all the y prime terms to one side, take all the other terms to the other side. So let's subtract xy y prime from both sides. That will bring all the y prime terms to the left, and then subtract y from both sides. So I move xy y prime to the left and y to the right. So now on the left I have only terms with y prime in them. On the right I have terms without y prime. I factor out y prime on the left. This is equivalent to the step of combining like terms when we solve linear equations. So on the left I have x minus xy times y prime equals xy minus y. I divide both sides by coefficient of y prime, namely x minus xy. That gives me y prime equals xy minus y over x minus xy. This concludes our first look at implicit differentiation.